Good morning, ladies and gentlemen. I'll start with a very, very brief sort of introduction. You can see company is Innocent. We specialize mainly in sort of quality assurance sensors and equipment for, I would say, three-piece mainly. We do some for two-piece, but it's mainly sort of three-piece. We started quite a while ago. Originally we're part of Sencon, split sort of amicably about 15 years ago, and have since gone our own way. The Innocent products at the moment are used by can makers in over sort of 70 countries, so we're doing sort of very well, fortunately, and I'd like to thank all of you for your support. We also, fortunately, have a lot of customers, friends, sort of in Thailand. Myself, very quickly, I've been sort of in can making for over 40 years. I'm an engineer, I love technical things, so for the sales pitch, I'm probably not the best person, but I'm going to try. What I'm going to talk about today is mastering coating control in sort of metal packaging. And before I sort of get sort of stuck in, does any one of you, and I want to see rising hands, want to make bad cans? Nobody. Well, that's actually pretty good, because I couldn't help you if you would. So if you do not want to make bad cans, the question is, how do you make good ones? And there are sort of many sort of aspects to that. The first thing is that you will need to define what a good can is, because if you don't know what it is, how are you going to make it? So the definition is not necessarily that it needs to be perfect, not at all. What you need to do is cans, you need to make them with such a quality that your customers want them, and they will need them sort of with such a quality that their customers want them. That's sort of the brand owners sort of want them. And that sort of applies to many different aspects of the can. It will be, for example, sort of the dimensions of the can. It will be the coating, the one that I'm going to talk about. It will be the print. But it would also be sort of mechanical things. Well, when it comes to the coating, it's the weight, it's the distribution of the coating, it's the adhesion of the coating, but then there's also sort of mechanical sort of things, the strength. So, a bit further, how do you make good cans? It's about the equipment that you have, the equipment that you use to check sort of your process, and then your procedures. And it's mainly sort of the SPC sort of that is going to be important in that respect. What does it stand for? It stands for Statistical Process Control. You all make cans in huge quantities, and it's impossible to measure every single one of them. So what you do is you take a sample and you kind of make that sort of applicable to the whole bunch that you've sort of produced. It's a bit like elections. You interview a few people and then you declare whatever sort of they sort of decide as the outcome of the election for the whole country. So we'll start with SPC, and I'm going to talk about a few sort of things that are used a lot sort of when we talk about SPC. First is a histogram, and the other one is going to be process capability. Histogram. Maybe all of you know it, but I'm going to do it anyway. So just imagine you've made loads and loads of sheets. You've got pallets full of them. And they're all supposed to have a film weight of 10 grams per square meter. But of course, they won't all be exactly 10 grams. Some of them will be a bit heavier, some of them will be a bit sort of less sort of heavy when it comes to the coating weight. So what we're going to do, we're going to sort them. So I'm marking sort of squares on the ground, and the ones that are 10, I'm going to put them in the middle, and the ones that are heavier, I'm going to put them over here, still heavier over there. So I'm going to sort them. And what will happen when you do that is, so these are my squares, sort of where I'm going to put them. And when you stack them, what you'll find is that the ones that have the weight that you wanted, that's at least if your process is sort of adjusted properly, that's going to be the tallest stack. You're going to have most of those. And the further you move away, either in positive sense or in negative sense from your target, the smaller the number of sheets that you will have produced is. Now, there's actually, if you look at it, this sort of has a kind of a curve that you could draw over your piles. And this curve is called a bell curve, or it's called a Gaussian distribution. Now, Gaussian distributions have a very interesting sort of property that was found out by this very clever German mathematician a very long time ago, Mr. Gauss. That's why this bell curve is also called a Gauss curve. Now, what's so special about it? There is some sort of math that you can use to come up with something called a standard deviation. Again, it's something that sort of sounds boring, but it's absolutely very useful. The sign for a standard deviation is that strange sort of Greek thing at the bottom. It's called a sigma. And what is this Gaussian distribution? Sorry, what is the standard deviation? You start with the average, and what you now want is, you remember we had sheets sort of piled up. So what I'm going to do is, between the two outer dashed lines, I'm going to sort of count all the sheets that I've got in that sort of line, in between my two lines. And I know how many sheets I've got in total, and I'm going to move these lines in and out until I have 68% of all the sheets. When you have 68% of all the sheets, that means that you've got plus and minus 1 standard deviation. So it's expressed in grams per square meter in this case, because that was my standard. It could also be sort of in microns, it could be sort of in milligrams per 4 square inch. But once I have my 68% covered, I have exactly plus and minus 1 standard deviation. Now, what's the nice thing about the standard deviation is that if I now take plus and minus 2 standard deviations, with 2 standard deviations, I end up with 95% of all my production, sort of within those limits. And if I do even more, plus or minus 3 standard deviations, I have 99.7% of my complete production covered. So that's really interesting that this guy found out. Now, how do you use that? First of all, these bell curves, they can have different shapes. You've got the red one, which is quite steep, and you've got the blue one, which is more flattened. If you have the flattened curve, you'll understand that you've got more sheets towards the plus and minus sort of areas that are more away from what you wanted. If you would have a very, very narrow sort of distribution curve, almost all your sheets would be perfect. They would be very close to the 10. Now, what you can do here is that you can add sort of lines, the LSL, which stands for the lower specification limit. That's the limit that you've agreed with your customers, that you're never going to make any sheets that have a layer thickness that is less than this lower specification limit. And on the high side, you can do something similar. You can have an upper specification limit. So you're not supposed to deliver any sheets that are beyond sort of the lower or the upper specification limit. Now, if you look at the red sort of curve, which is a sample of the distribution that's relatively narrow, you see that beyond the lower specification limit and the upper specification, there's still sheets. Now, these are the ones that you're not supposed to send to your customer because that's outside of what you've agreed with them. Yeah. Now, if you would have a production process that responds more to the blue curve, you see you have many more sort of that outside the specification limits. Now, if your process really would be like the blue curve, and those lower and upper specification limits would really be what you'd agreed with your customer, you would have loads of scrap. Well, first of all, you'd have to identify the sheets that are wrong, but there's absolutely loads of them. So this is going to be a very expensive way of operating sort of your plant. You really need to make sure that everything stays within the upper and the lower specification limit. And how do you do that? You need something to measure sort of your sheets. And what systems exist? There are sort of those systems that work without making contact with the sheets. As I said, I'm mainly talking about 3P, so we're talking about a sheet coating line here. The non-contact systems, they're either spectrophotometric or the interferometric. Sencon sort of sells the first one, sort of Specmetrics sells sort of the second one. They both work very well. They're super expensive. What they do, they measure a strip on the right-hand side and on the left-hand side of the sheet. And and to make sure that you do not have too much noise in the signal, which means that the indication would vary like crazy, the average over a number of sheets. So you get a really stable sort of indication of what your weight is, left, right. So you can use that to adjust the balance of your machine. You can also use it to go up and down. So machines work, as I said, really well. Then you have sort of systems that are contact. The poorest one is right at the bottom. It's ultrasonic. It's mainly used in automotive. It's for thicker layers. It's got a very poor R&R. I'll explain later what that R&R is. Gravimetric, it's accurate, but it's destructive, so that's not very useful. And then you have the capacitive system that Steve spoke about. It's not as accurate as the non-contact systems, but it's cheap, and it's kind of the industry standard still. And that's for a reason. The non-contact systems, they're super capable. They can actually sort of measure sort of nanometer type thicknesses. But there is no machine in the world that has a button that you can just adjust to achieve the last nanometer of thickness. I mean, you're lucky if you get plus or minus a gram per square meter. So you don't need that ridiculous accuracy, but you are paying for it. So that's not necessary, but there's some other sort of things that come into play. I said I'm going to talk about R&R. I'll do it very, very quickly because, of course, time is always an issue with these presentations. Every measurement system, no matter what it is, has errors. And if you have a measurement system that has a big error, and you try to adjust your process, you sort of bring that error into the process. So if you have a process that you want to control within very sort of small limits, you need to make sure that your measurement system has an error which is a lot smaller than what you're trying to achieve with your process, otherwise you're never ever going to get there. And there are sort of examples where people adjust processes using sort of systems that have a poor R&R, and they basically just keep on adjusting, they never achieve sort of anything. So repeatability and reproducibility, that's what R&R stands for, super important. The non-contact systems certainly have a very good R&R. The capacitive system also has good R&R. Typically what you want, and a way to think of it, it's not statistically speaking correct, is that you can say that this percentage, R&R, and the smaller is better, is kind of the error in the measurement system expressed as a percentage of the process that you're trying to control. So if you're trying to control the process to plus or minus 1 gram, you want a measurement system that has an error which is smaller than 10% of that plus or minus 1 gram. If the error, they've made something here to trip me up. If the error is, so if the R&R is between 10 and 30%, maybe acceptable, depends on what other systems might be available and what you're going to use it for, but not recommended. 30% or bigger, you're wasting your time. This is very often the case with, for example, viscosity measurements. People have these little things. You ask one person to measure it, you ask them, you get totally different results. You're basically wasting your time. So that's the idea of this. Then systems with good R&R. As I said, the non-contact ones, they're all good. The capacitive ones can be good, depends on where you get them from. Capacitive, in terms of the results that you get for the money that you pay, is at the moment, I would think, still the best that you can do. It's not real time. You have to take a sheet off the line, it needs to be dry, and then you need to measure it. Not necessarily a huge problem, because the process that you're trying to control has a relatively big time constant. So you don't need super fast feedback, because your process doesn't change that fast. Part of normal control theory. For live startups, it's different. If you have to wait for a first sheet to come out of your first oven door before you can measure it, you are wasting production time. The non-contact systems, you get immediate feedback, so if you have a lot of changeovers, they have a good payback. But that's not the case for everyone. So capacitive measurement, what's important there? They all have a rubber probe tip that pushes down sort of on a metal sheet. The gold layer is the lacquer layer in between, and they're basically forming two plates of a capacitor. Formula here, so the capacitance, epsilon times the surface area of the probe tip, divided by T thickness between the probe tip and the metal substrate. I need to go quicker. During calibration, sort of the dielectric constant and the surface area are measured. You put those as a constant sort of into your gauge, and now by measuring the capacitance, you can see what the thickness is. Now it's important that that area of the probe tip doesn't change. So what's important, you need to keep your probe tip sort of clean. You need to make sure that it deforms and stays deformed where is important humidity. And when you have a calibration sheet, don't just use a single point to make your calibration, use multiple points on your calibration sheet. It helps your accuracy enormously. Deformation, why is that important? When you fit sort of a new rubber probe tip and the probe tip weight starts weighing down, the probe tip deforms. It actually expands. It becomes like a mushroom. Now, during measurements, the relaxation is small, so in between measurements, you do not notice a difference. But when you fit a new probe tip, you need to let it sit on a solid surface for 30 minutes before you do your calibrations, because if you don't, it will change afterwards and your readings are all going to be out. So that's important. I've seen customers that were very careful with their equipment and parked their hover probe on a mouse mat that's soft. That means that you're sort of getting relaxation and it goes wrong again. You need to keep sort of your hover probe on a hard surface. Systems to have. This is the one that you'll find sort of in most factories in the world. This is the second version that we've made. It's been around for probably around 25 years. And as I said, this is a better version. This one doesn't require a crocodile clip, so you don't damage your sheets. You can put them back on, if sort of your standards allow, you can put them back on the production line, and you would save sort of a lot of money in the process. So I'm going to skip through this, it's quick. We made something else that you can use to measure tubes, and you can use that to also measure severely necked in sort of monoblock sort of cans, also capacitive. Now the next thing, and that's very important, is that you've got these gauges, they produce loads of data, but what are you going to do with them? You've got all these numbers, and how do you use them to actually adjust your process? Because if you've got all those numbers, and I remember a project a long time ago that would produce sort of almost a cubic meter of paper sort of every week, nobody had time to read that, let alone sort of analyze it to then conclude what kind of an adjustment you needed to make. It's almost impossible. A lot of people still write all these data down, and then all the piles go into a lever arch file, and that's it, nothing ever happens. What you need is a way to actually analyze all those data points. You don't need data, you need information. You need to know what you need to do with those data. That's why we developed this software called Innolytics. It at the moment works exclusively with the Sencon sort of film weight gauge. What it does is it first of all makes a graph, that's the one that you see at the top, with all the data. You can sort of analyze per operator, per shift, per channel number, per lacquer type, per job if you want to. And then you can search through those data sort of at a later point. If data go over the upper and lower specification limits, the screen will start flashing red, and you know you need to stop sort of production or sort of at least introduce hold for inspection. There's also control limits, then it will flash sort of yellow. It will record the person that made that measurement, and now you immediately have to do something like sort of measure more sheets, and you can see what time it takes, who does that. It's all sort of available. Now, super important, we, as I've said, have these live data here with the dotted lines, the outer ones, the specification limits, the inner one, the control limits. That's where the operator needs to jump into action and do something. But what we've also got are sort of things to help you analyze the data at the bottom. This here is a representation where we measured sort of 9 sort of dots for every sheet. And the first set of sort of data here is the mean of each point measured over many, many sheets. So if you, for example, are measuring and your operator has a few points that are too heavy, sort of like here on the right, does he immediately go to the machine and adjust it? No, he shouldn't. But if that happens all the time, well, then perhaps he should look at it. The next one is the standard deviation, and not for the complete sheet and all the sheets. No, this is per point. So if you, for example, see that the standard deviation on the left is really low, but the standard deviation on the right is really high, that could mean that your bearing on that side is out. And your sort of roller sort of is hydrostatically lifted by the lacquer layer trying to squeeze underneath, and you get sort of a big variation on that side, but not on the other side. You can see whether the barrel shape, if your rolls is correct. You can see all sorts of things by actually analyzing that data more than sort of what you would normally do. Few more graphs here. As I said, you can do this per shift. You can go back in history if you have a complaint. Everything sort of is recorded. You can make custom tags. So if there's certain things that are specific for your factory, you can also do that. It's all sort of included. Yeah, this is just sort of a bigger sort of representation of what we saw before. So you got the mean, you got the standard deviation, the minimum, and the maximum. They're all color-coded. So these are the two sort of really important ones. And we believe that nobody else sort of represents sort of the data like this far. So with this information, you should be able to get your process under control sort of a lot better. It also, of course, makes these curves. It does box and whiskers sort of to see whether you've got outliers, how big they are. It's a typical sort of SPC program. So, conclusions. You need to have equipment to measure your process. The equipment needs to have a good R&R. Ideally, you will be able to measure multiple points on your sheet, because if you only measure left and right, you're missing a lot of sort of information that you would need to actually adjust your process properly. You can do that with the non-contact systems, but that's not typically what they're used for. The capacitive ones are very suitable for that. They do have a good R&R. So, HoverPro with the analytics software, I would say that's an ideal combination. Ladies and gentlemen, thank you. Hope it was interesting.